Writing tests in Go, like writing anything in Go, can look and feel pretty different to other programming languages. So, today, I want to share with you some of the tips and techniques I've learned over the years when writing tests for Go. First things first, how do tests actually work in Go? When you run go test on the command line, or when you press the Run Test button in your favorite IDE, Go compiles the source files of the current package, along with its test files, into a test binary. That test binary then runs through every test function it can find. It then reports the results of each test, pass, fail, or skip, and you, the developer, can use that feedback to go back and fix your code. Already, there's a couple things worth mentioning about this process. When you're not running go test, say if you're running go run or go build, Go doesn't just ignore the test functions you've defined, it actually ignores all test files. In any circumstance when you're interacting with the tool chain other than running go test, Go will deliberately ignore any files that end in _test.go. Not just the functions, I mean absolutely all of the code in those files. That means init functions, variable declarations, imports, everything. They're basically not there. This has some really interesting consequences that we'll get into soon, but what I want to make clear from the outset is that the only thing that makes something a test file is its name, something_test.go. Now, Go also offers a special test package that's allowed to coexist with its associated package code. So, for example, if you had a package called foo, you could, optionally, define some files in the same package that are assigned to package foo_test. It's a useful feature in some relatively obscure circumstances, like, for example, it's hard to test the fumped package without those tests themselves using fumped to print out messages and so forth. So, to avoid that import loop, fump's tests are defined in the special fumped_test package. But unless you're specifically trying to avoid an import loop or some other problem like that, you do not need to define your tests in a test package. Defining them in the same package with a file ending in _test.go is all you need. So, now let's talk about those tests. What makes a good test? Well, I think the most important property of a good test is consistency. That is, no matter how many times you run the test, and no matter what order the tests get run in, the output should be the same. It should be reliable. If you don't do this, you have what's known as a flaky test. And flaky tests kill productivity. Even if each individual flake is relatively rare, combined with lots of other rarely inconsistent tests, you will get inconsistent results very often, which can be especially time-consuming when tests are part of a longer process like a build pipeline. But you can protect against this. How? Well, when you run go test, don't just run go test. Run go test with the race detector and the shuffle flag turned on. This will run the tests in a random order and also alert you if there are any data races. In other words, if there's a variable under test that gets read from or written to by multiple Go routines without synchronizing in some way first. If you're stuck diagnosing one of those rare flakes, you might also find it useful to add the count flag to your go test command. This controls how many times the tests get run. Set it to a high value, like 1,000 or 10,000, to run the tests over and over again. If your tests pass with a high count value, especially if you're also shuffling their order, you should be pretty confident that your tests are both consistent and reliable. While tests need to be consistent, one of the misconceptions I often hear is that they need to be parallelizable. That is, capable of running in parallel with other tests in that package's test suite. Parallelization can be nice, and if you've got a test or a set of tests that you're confident can run in parallel, go ahead and mark them as parallelizable. But in most circumstances, this isn't really worth optimizing for. That's because if you're writing tests correctly, most of your tests are going to be fast, like really fast. Even if you've got thousands of them running sequentially one after another, most of what your test should be doing is just checking some logic, and computers are very, very fast at doing that kind of work. So, if you've got a slow test, you'll get more benefit out of fixing whatever is making it slow, instead of trying to refactor it just so it can be marked as parallel. So, what do these tests look like? Well, most tests are functions whose names start with the word test, followed by a description of what's being tested inside that function. And the test function takes one parameter, a pointer to a testing.T. When something unexpected happens in the test, it should call t.Errorf to report what's gone wrong. Alternatively, if there is no way for the test to continue, it should call t.Fatalf instead, and the test will fail out early. If a test runs to completion without having failed, it's considered passed. And that really is the basics of how a Go test works. But there are way more tools available here than just marking something as failed or not failed. I highly recommend checking out the documentation for that testing.T type that gets passed into each test function. It's got a lot of really useful things on it. One of those useful things is called t.Cleanup, which registers a function to run at the end of the current test. Now, if you're a seasoned gopher, that might remind you a bit of the defer statement, and it's kind of similar, but it has a lot more flexibility. Tests often make use of additional helper methods that might create resources that then need to get cleaned up at the conclusion of a test, or they might change some state that should be restored to how it was at the beginning of the test once the test ends. That's hard to arrange with just defer statements, but it's easy to do by passing around the testing.T and letting helper methods register their own additional cleanup steps as needed. So you can think of t.Cleanup as serving a similar purpose to defer, but with a test-wide scope. In general, you should default to using cleanup instead of defer statements in tests, except in cases where you definitely have to use defer, like capturing a panic, for example. By defaulting to t.Cleanup, it makes restructuring your tests that much easier later. For example, if you discover that you have some common code that you'd like to pull out into a helper function. Testing.T also has a lot of functions that automatically register cleanups too, like t.setEnv, which sets an environment variable to the value that you specify, and then reverts it back to its original value once the test is over. Or if you need a temporary directory, use t.Tempter. It will delete the directory it created once the test is completed. Basically, if you have some state that you want to do and undo, well, first, it's worth looking at testing.T to see if there's already a function on it that can help you. Otherwise, use t.Cleanup to register the undo part once the test is over. You can also use testing.T to mark a test as parallelizable. To do that, just call t.Parallel at the top of the function. But, like I said earlier, only do this when it's convenient. Don't go refactoring tests just to make this possible. And another handy thing you can do with testing.T, you can check whether the short flag has been passed to the go test command. So far I've been speaking in pretty broad terms about what a test should look like or what most tests should look like, but the fact is, depending on the program you're writing, you may still have some part of your test suite, hopefully a very small part of your test suite, that has to run more slowly. Like, you might be integrating with a remote system or a local container that you need to spin up that takes some time to get going. These are the kinds of tests you should skip if the short flag is enabled. It's actually really easy to do. At the top of your test function, check for the value returned by t.Short. If it's true, and the test you're writing is meant to take a little while longer than average, you can, and please, should skip it by calling t.Skip. Please distinguish between short and long tests in exactly this way whenever you can. Being able to run a short test suite in under a second or two is a really, really powerful feedback loop to have while you're making changes. Another useful method on testing.T is t.Run, which lets you break out into a subtest. Subtests are pretty much what they sound like. Tests running inside the scope of another test with their own unique names and their own pass, fail, or skip results. T.Run works really well with another testing concept known as table-driven testing. Sometimes, when you're writing a lot of tests, you'll find that a lot of those tests look very similar and only vary in their inputs and their expected outputs. Table-driven testing is a way to have multiple test cases share the same logic and break the inputs and outputs out into their own table. Then you iterate through that table using subtests. By table here, what we really just mean is a struct, typically an anonymous struct, which defines lots of different test cases. Writing tests this way makes it easier to both read the test cases and to modify existing ones or add new ones. This is especially useful when the testing logic gets really complicated. Being able to identify exactly what is under test and exactly what is failing is really important. One of the things that you can define in a test table, if it makes sense to do so, is a name for the subtest you're going to spin off. It's often useful to just toss a string into the struct definition that describes the scenario that's going to be tested, and then to use that same string value as the name of the subtest. This helps a lot with readability and maintainability over time, especially as the number of test cases grows. I found that, in general, it's best to keep the table simple and make the test complicated instead of the other way around. The test table should, as much as possible, just be plain old data, and not, for example, a bunch of function literals that are adding ad hoc logic to different cases. Your mileage may vary on this, but I find it's useful to default to adding more complexity to the test rather than the table. Now, when you're iterating through lots of cases, like when you're using table-driven testing, it's really important to not stop your test at the first failure. I'm sure we've all had the experience where you're working on a test and you get a failure back, and then you fix something and you get another failure back, and then you fix something else and you get a third failure. And at that point, it dawns on you that something's probably wrong at another level, either the test logic or, more likely, the code you're changing. And this is because tests that fail early don't give you the complete picture. For this reason, it is important to prefer using t.Errorf to t.Fatalf. Obviously, there will be scenarios where it's definitely not possible for a test to continue because some necessary precondition has failed, but in general, default to marking something as an error rather than stopping the test entirely. This does mean that you can end up with a lot of test output, and in my opinion, that's a great thing. Just make sure that when you do call t.Errorf, you provide a reasonable amount of context for anybody looking at the test output. This usually means identifying the function that was being tested along with any relevant inputs and outputs. One of the idioms that you'll notice over time in Go tests is the idea of got versus want, or the output the test got versus the output it expected. It's useful to refer to these two concepts by their well-known got and want names in the test output, and they're also great variable names to use in the tests themselves to represent exactly that. Of course, Go is a typed language, which means you'd normally only get one got and want variable per test, but this is where another feature of Go, if with a short statement, really shines. Whenever you declare variables in an if statement, those variables only exist within the scope of that if statement. They actually carry into the else branches as well, but as soon as the if statement is closed, those variables are gone too. Which leads to a really common testing idiom that is useful when checking a condition. Start with an if, declare a got and a want variable set to what you got and what you wanted, perform the check that you're interested in, and if that check fails, print out those same got and want variables alongside the function that failed the check. This has the advantage of making what's going on very clear to anybody who's reading the test code, but it also prevents you from having to repeat the got and want values when printing out the test error, which protects you from the test output being potentially wrong. Like if you type out the desired value in one place, but printed a different value in the output. Now, those of you who have written a lot of tests in other languages might wonder why this idiom needs to exist at all. After all, other languages often have assert libraries that let you define what you got and what you wanted with no redundancy whatsoever. Wouldn't that be better? Shouldn't we use one of those here? Actually, assert libraries are kind of an anti-pattern in Go tests, which surprised me when I first learned it. When I first started writing tests in Go, I went looking for an assert library because, well, I got used to JUnit style testing being the norm pretty much everywhere, no matter what language I was working in. But it turns out you don't actually need those. If anything, assert libraries end up hampering readability and control flow more than they end up helping. The Go wiki goes into some more detail about this, but the argument boils down to essentially this. It doesn't make sense to have a completely different DSL or domain-specific language that's used only in testing. There is already a perfectly good language available for writing test logic in Go. It's called Go. In other words, test code should look and act pretty much just like any other Go code, and assert libraries take away from that. For example, imagine you want to assert that some variable foo is equal to 42 in a test. You could do that with a DSL function like assert equals and call it with t and foo and 42, or you could just write if foo is not equal to 42 and make an error happen. Both of these things describe the same check, but the latter is written in regular Go. You don't have to switch your brain to this other non-Go language to understand the flow of the test. And I realize that JUnit style testing can feel very normal, especially if you're coming from other languages that use it. But my advice is this. Try writing some tests without it. You might find that there's a lot less friction than you think. It also gives you significantly more control over what the test is doing. Assert libraries in particular are notorious for exiting on the first failed assertion when, like we talked about earlier, a good test should print out as much diagnostic information as possible instead of stopping early. Moving out of assert functions and into regular if statements gives you control over whether you want to call t.Errorf, t.Fatalf, t.Skip, or do something else entirely. A test function is, after all, just another Go function. Also, if you think about it, it's a lot more Go-like for branching logic to be made explicit, and errors and fatals almost exclusively happen in branches. It's kind of bringing the same error handling philosophy from normal Go code into test Go code and aligning the two. But what about comparing big and complicated types? Surely assert libraries are good for that. In fact, this was actually my personal hangup and the reason why I held on to assert libraries for way too long. But it turns out there's another way to do this. In fact, there is a library created specifically for handling this problem. A library owned by Google, in fact. You can find it at github.com/google/gocomp. The output from this library is downright magical. It is really, really good at identifying the parts of the values that you care about and skipping over the parts that you don't, even if you're comparing two very complicated and deeply nested structures. It also has one of the best designed configuration systems that I've ever seen for any comparison library. I really encourage you to have a look at its documentation. If you want to ignore certain types, or always consider certain types to be equal, or ignore a degree of floating point precision, or even perform your own special equality logic on a type, all of that is available. It's really extensive, it's well thought out, and it's better than anything I've ever seen from any assert library. The main functions you'll be interacting with from this library over and over are comp.equal and comp.diff, and they do pretty much what they sound like. First, you check whether the value you wanted is equal to the value you got, and if not, you print out a human-readable diff that diffs between what you got and what you wanted. This works well with the overall got and want pattern we talked about earlier, and you'll find that handling a complex equality check now looks and acts very much the same as a simple equality check. You can find a lot of the stuff I just talked about, plus even more, on the Go wiki under the test comments page. That page is a great resource and contains a lot of wisdom that you can link to people at code review time to help them improve their own Go tests without having to go and re-explain everything yourself. Now I'm going to move beyond what's available on the Go wiki and start talking about the more complicated topic of faking stuff. Now, why would we want to fake stuff in tests in the first place? There is a fantastic talk about this exact issue called Beware the Integrated Test Scam by J.B. Rainsberger. If you haven't seen it, add it to your to-watch list. It is amazing, and I think it speaks to a lot of deeper truths about testing that I will breeze past and do my best to summarize in this section. Basically, your program is made up of individual systems that we'll call units. There are lots and lots of code paths and interdependencies between these units. And if you try to only test your programs at the edge boundary, that is, you don't fake anything inside at all, it's really hard to exercise all of these code paths that are nested deep inside your program. In fact, it is a factorially hard problem, and more tests do not solve it. Also, integration tests are slow and fragile. The feedback cycle is less than ideal. And if all you have are integration tests, or if your test suite is weighted a bit too much in that direction, you'll know the frustration of making a change, watching all the tests go red, and then spending way too much time figuring out which part of the program actually needs to be fixed. Because when all your tests are happening at the most broad scope possible, it's very hard to correlate test failures with individual components of the program. And in my opinion, that destroys a lot of the value of testing your code. Now, I'm not saying that you should have no integration tests, or it's just that you should have way more unit tests. Lots and lots of tests that effectively lift pieces out of the overall system and test them independently, plus a few broader scope tests that check how they all work together. And the only way to reliably separate out parts of your program from one another is, in one way or another, to fake stuff. I found it wasn't obvious to work out how to do this in Go. I'd mostly worked with interpreted languages previously, and usually there's a popular library or two that'll let you stub out just about anything you can imagine, whether that's first or third-party code. But Go is a compiled language, and it doesn't run in a virtual machine, so faking stuff isn't quite as straightforward. And so people have come up with their own solutions and rules to try to work around this problem. You might be familiar with this one: accept interfaces return structs. Or maybe you've heard it as accept interfaces return types. I suspect that this piece of advice springs from the exact same difficulties I'm talking about right now. We need to be able to fake stuff in order to make testing certain things possible. But how do we fake stuff without modifying the code too much? Well, interfaces seem like a pretty reasonable solution to that problem. If your code accepts interfaces, then you can create new types at test time that fulfill those interfaces, and that solves the faking problem, right? Except it creates so many new problems. Now you have to implement this rule pretty much everywhere in your program. And that means using interfaces where interfaces don't really make sense. You have to permanently change the way in which you write your code in order to make it testable. In other words, testable code now looks fundamentally different from other normal Go code. And that should make you suspicious. See, Go interfaces are not like other language interfaces. Go interfaces are implicitly satisfied, which means it is deliberately very difficult to go from an interface back to its implementations. And this is by design. If I have an io.writer passed into a function, I really should not care about what its underlying implementation is. Maybe it's a file, maybe it's a network connection, maybe it's a serial cable that goes to an Arduino. It does not matter. And it shouldn't matter. But in a world where every single one of your functions, no matter what it's doing, accepts only interfaces, well, those implementations are definitely going to matter, at least some of the time. You do really care about what gets passed in, and code bases with lots of interfaces everywhere become really frustrating to read and work in for that reason. Go interfaces are a deep topic that I plan to dive into in a future video, so make sure to subscribe if you're interested in that. But to try to give you some flavor of how they should be used, I'll give you this rule of thumb for the time being. If you need to reference a specific implementation of an interface in order to get useful work out of it, or if you end up copying and pasting lots of function signatures to try to fake something, you're probably getting all the downsides to using an interface with none of the things that make them really powerful. So, if the answer isn't interfaces everywhere, what is it? How do we fake stuff in this language? Well, let's talk about the easy stuff to fake first. The easiest thing to fake is actually functions from external packages. In Go, functions are just values. That means you can take any function you like, assign it to a variable, and then call that variable rather than calling the actual function. For example, say you've got some code under test that uses time.sleep. You definitely do not want to be calling time.sleep in tests. Even a brief sleep would make your test orders of magnitude slower than it should be. What we can do instead is assign time.sleep to a variable called sleep, for example, and then call that variable everywhere that you would normally call time.sleep. This does make testable code look slightly different from normal code, and it does add an additional layer of indirection. But it's a very thin layer. One that a quick jump to definition or even a grep could solve. And if you choose your names well, you can make it reasonably obvious what the real function is that you're calling. So what about package local functions? You could use the same trick, but that would mean making a separate function value for every function that you want to fake, and you'd have to be very, very diligent when writing your code to make sure you're never calling the real underlying function. I think that's a bit more confusing to do when it's all happening within the same namespace. But we can do something adjacent to this that's clearer. Define a private variable or a field with a function signature that matches the signature of the function you want to fake. This is our test hook function, and conventionally the variable name should begin with test hook. So if I wanted to create a hook for the function greet, for example, I'd call its variable test hook greet. Then add a guard at the top of the function you want to be fakeable under test. If the test hook value is nil, as it will be during normal operation of your program, the function will execute normally. If the test hook value isn't nil, however, it'll run the test hook instead. When you call the real function, so long as the test hook hasn't been set, it still runs normally. But during test time, you can set and unset those test hooks as you need them. This is a trick I picked up from the Go standard library. Even within the standard library, there are dozens of these test hooks scattered around to solve the exact same problem we're talking about right now. Sometimes you just gotta fake stuff. This might seem like a strange approach, but it's really another example of explicit branching. And I think that's one of the themes of Go overall. In the same way that you write a 3-line stanza when you check errors, you also write a 3-line stanza when you check for test conditions, and here you write a 3-line stanza to potentially override function behavior. And really, this is the same thing that's happening under the hood in those mocking libraries in other languages. Mocking stuff is just a matter of saying, given this condition, run this, not that. It's just that, in Go, like everything else in this language, we write it explicitly. If you're concerned about the performance cost of checking a test hook at the top of a function, have a look into profile guided optimization. Not only will it optimize these branches, it will also optimize any third parties functions with similar checks, and it's just going to make your code run faster in general. Also, if you're interested, I do have an experimental code generator at lasso.io/testdetect that tries to get test-related branches compiled out altogether. It works with both GC, the primary Go compiler, and TinyGo. Profile-guided optimization is still a much better general solution, but I'd invite you to have a look at the package if you're curious. And pull requests, as always, are welcome. So now we know how to fake third-party functions, and we know how to fake first-party functions. But there's still one more topic about faking stuff that I happen to think is one of the topics we, as a community, actually have the least guidance on. I'll talk about my idea for a solution here, but I'd love to hear some of yours too, because I think this is a real problem that needs solving. And that problem is client libraries. You know them, you use them, and it is nigh impossible to talk to a complicated third-party API without them. By client libraries, I mean stuff like the AWS SDK, a GitHub API client, a Discord library, packages that exist to abstract away the gory details of some API somewhere so that you can have a better and more type-safe experience working with an external service. I haven't been able to find any satisfying solutions for faking these. You could wrap them in your own package local methods and then add some hooks to those methods. You could assign all the client methods you plan to use to package scoped variables. But either way, it ends up being this bookkeeping nightmare with lots of copying and pasting. And interfaces don't really work either. On top of everything I've already talked about with interfaces, client types often have dozens to literally hundreds of methods defined on them. Even if you define a big interface that has only the methods you plan to use in the program, it's a lot of toil. You could try faking the server the clients are talking to, and in fact, I have seen Go code in real professional environments that tries to fake things at the HTTP layer. But in my opinion, this totally defeats the purpose of using a client library in the first place, because now your tests are forever tied to the exact details of the API the client library is supposed to abstract away for you. So, given the current state of things, here's my attempt at it. Go is this wonderful concept called struct embedding. It's a really powerful way to compose multiple types together. When you embed a type inside of a struct, any methods that are defined on the inner type and not defined on the outer struct are promoted at compile time to work on the outer struct. This isn't like a trick, it's not like a weird quirk. This is actually something that is core to the language, and it's in the language's spec. It's got a lot of interesting applications that I might go into some other time, but for now, we're going to focus on how this gets us to a point of being able to fake stuff. Remember way earlier when I said that Go ignores test files if you're not running tests? Combine that fact with the fact that you can define methods anywhere you like, and you have the ability to conditionally define methods on a struct at test time. In effect, this lets us intercept method calls on package local types. I wrote a code generator to take advantage of this fact. It's called lasso.io/moxie. Its API is deliberately as simple as I could get away with. Basically, you can choose to override one or more of the type's methods with your own logic. I'll take you through an example. Say I have an S3 client, and I want to be able to intercept its method calls in a test. All I have to do is define a package local S3 client type that embeds the real S3 client. I'll call the package local type S3 client to make the code I'm using it with as clear as possible. Then I add a go-generate command to create proxy methods for my package local S3 client type. When I run go-generate, a new test file pops up that defines methods on S3 client, which I can then optionally choose to mock in a test. Now, I can write my code normally and mock the client methods under test when I need to. So for example, if I wanted to fake the output of a list bucket on my client type, I could use a special generated method, _listBucket_return, to intercept that call and have it return whatever I wanted. The code generator only generates methods inside of test files, so these overrides can only exist at test time. That means you can never accidentally run a mocked function during the execution of your main program. Also, since method promotion happens during compile time, not runtime, there is no runtime method dispatch overhead to be concerned with. Embedding a type in another type, as far as I can work out, really is free. If you also have difficulty with making mockable but clear client API code, please give Moxie a try. Feel free to open up GitHub issues for your own user experience reports, whether they're good or bad. And if you find that it doesn't work for some type or other that you want to use it with, please file a bug report. I'd love to fix whatever bugs you run into so we can get this to a point of being ready for version 1. Alternatively, if you've got another more elegant way of handling these sorts of complex types, tell me about it in the comments below. Maybe Moxie isn't the right long-term solution. But if putting it out there inspires a better one, I'd be just as happy with that outcome, believe me. And that's probably enough about writing Go tests for now. There is so much more to talk about that we haven't even scratched the surface of in this video. There's fuzzing, there's benchmarks, there's testable examples, there's test main. I'll probably cover one or more of those things in future videos, so get subscribed if you're interested in learning more about Go testing, or even just about Go in general. I'm also starting up a Discord server. If you'd like to chat with me about programming languages, feel free to join it. It's at lesu.dev/discord. If you're interested in supporting this channel and you'd like early access to future videos, drop a subscription at lesu.dev/Patreon. And finally, I just want to leave you with this thought. You might be coming out of this video realizing that there is a lot about your tests that you might want to change, or just a lot of new things that you might want to try. Don't feel like you have to go back and rip out a bunch of working tests. If they're providing value for you, that's good enough. Instead, just focus on writing your next test differently. Try writing a test without using an assert library. Try writing a test with a test hook instead of using an unnecessary interface. Try using a test table instead of writing lots of individual functions. Just give it a shot and see how it works. You might be surprised at what you find. Until next time, I've been Chris Lesu. Happy hacking.